Good morning. My name is Jaeyeon, and I'm from kinesthetic lab. Today I will present TORC, a virtual reality controller for in-hand high-dexterity finger interaction, which is my internship project at my Microsoft Research, and these are my mentors, Mike Sinclair, Gonzalez-Franco, Eyal, Ofek, and Holz. Imagine that you have a skill ball in your hand. You will hold the ball with your fingers. You will use your fingers to examine its material. You will skillfully control your fingers to manipulate it. Then you will let it go by extending your fingers. However, most of the VR controllers we use are based on arm or wrist movement. You grab it stably and move it to interact or feel a virtual object. So, the interaction may be more like this. You have a tool in your hand and move your arm for task, not like the precise manipulation you do with your fingers. Of course, some VR controllers, like the Vive controller, have a touchpad, and it sends finger movement and use it to control parameters. However, compared to the real-world interaction, the touchpad always works the same. It does not differentiate the thumb movement for examining textures from that of rotating the object. And the haptic feedback does not change based on the virtual context. These are samples of prior work that enable grasping, touching, triggering, feeling texture, etc. in virtual reality. However, these devices are complex. It is hard to apply for mass production, and they have limited in-hand interactions. For example, to feel the texture or manipulate a virtual object, the user is required to move the whole controller instead of just move fingers. So, to enable in-hand finger interaction and finger-based haptic experience, we created TORC, a rigid controller that utilizes force between the thumb and fingers and thumb movement for interacting with a virtual object in hand. Before going into TORC interactions, I will first explain TORC hardware. It has a force sensor that senses the force between the thumb and two fingers, and it has a touchpad that senses the thumb movement. It has two wideband voice coil actuators underneath the finger mount and the thumb mount. The location of VCAs has been decided by a preliminary study. Special inclusion of TORC is the force bias and the fingertip capture. We made a little idle bias to the force sensor so that it can sense the finger extension or outer force when the user lifts their fingers from the device. We rendered haptic illusion of compliance using Kildall's method. A grain feedback made of 1 millisecond impulse was played when the first changes exceeds grain threshold. Those series of grain feedback mimic deforming vibration of an object. Now I will move to TORC interactions. In the natural interactions, we grab an object using finger flexion. With slippery force, we move our fingers on the object to feel the texture. We use deformable force to explore the compliance of the object. And with frictional force, we move our fingers to manipulate the real object. Finally, we extend fingers to release the object. Among all these interactions, those in-hand interactions of exploration and manipulation of an object continue seamlessly. Now, what do we want to do with TORC? We want to do the same natural interaction in virtual reality. Grab an object, feel the texture, feel the compliance, and turn it to see the backside, and then let it go seamlessly. In this table, low and high means the level of force. Yes and no means the existence of the modality. If there is a low-level force or touch and no finger movement, TORC presents visual rendering of grasping. This video shows the hand posture rendering based on inward and outer forces. See the real fingers and virtual fingers. Now I'm giving inward force. Now I'm giving outward force. Inward force twice and outward force. If there is slippery or light level of force and finger movement, TORC presents visual rendering of thumb movement and texture feedback. The texture feedback is changed according to the speed of thumb movement. As I move my thumb faster, the amplitude of noise signal becomes higher. If there is deformable, a high level of force and no thumb movement, TORC presents visual rendering of compliance and haptic illusion of compliance. This video shows how visual rendering presents compliance. The amount of deformation is calculated by Hooke's law. This video shows compliance feedback. The soft material between fingers and the device was used to visualize force changes. You will hear the sound of grain vibration. If there is frictional or high level of force and the finger movement is used to manipulate the virtual object. Haptic rendering can be presented depends on virtual context. For example, if you are turning a key or knob, then TORC gives you ticking vibration for each certain angles. Finally, if there is a negative extension force, TORC releases the virtual object in hand. This video shows the visual rendering of releasing object. Among the in-hand TORC interactions, we had interest in the effect of finger-based interaction on precise manipulation, and the effect of finger-based interaction on hand familiarity in virtual reality, in compared to the wrist or arm-based interaction. We conducted a user study to compare the TORC interaction with that of the original Vive controller. The task was two-level dexterity task, and after completing each condition consists of 20 trials, we asked the participant to answer embodiment questionnaire and to provide their preference. The first task was locating. In VR, there are key and keyhole. We asked the participant to align the key to keyhole. When they are well aligned, the participant presses a trigger button in their left hand, which is out of screen. Then, the key and keyhole changes into an asymmetric design. Now the user have to rotate the key to align the key and keyhole. When they feel they are well aligned, the participant presses the trigger button again. The same procedure was performed with Vive as well. We measured the task completion time for each of those tasks, and calculated distance and angular errors in the task. There was no significant difference in task completion time between torque and vibe. However, in both locating and rotating tasks, torque showed less distance and angular errors. The effect was even greater in angular errors in rotating tasks. Among the full 25 questions, 7 questions related to hand ownership, touch proxy, and ergonomics show differences. In this graph, score 3 means a strong agree, 0 is neutral, -3 means a strong disagree. Torque showed advantage in hand ownership. People actually believe that the hand in virtual reality as their own hand. For example, with torque, people thought the virtual hand as their own hand, but they thought the opposite with vibe. Also, they felt that the real hand was turning into virtual hand with torque, but not with vibe. Torque showed advantage in touch proxy too. The participant felt touch of the key in the location where they saw in the virtual fingers. Where they saw in the virtual fingers touched while they didn't with vibe. Participants felt like their own hand is touching the key with torque, but not with vibe. Also with torque, the participant felt a sensation in their hand when they saw the key turning, while they didn't with vibe. Finally, when they are using torque, the participant felt that their hands are located where they saw the virtual hand, while they didn't with vibe. In summary, we presented torque, a rigid controller enables dexterous finger-based interaction and exploration of virtual object. It gives rich degrees of freedom to the fingers on virtual object between forceful to light touch and between normal and tangential movement. Torque is a good proxy for precise manipulation, while maintaining a high level of hand ownership and ergonomics. Torque has low cost, low complexity, and robust hardware for mass production. We hope this paper motivates future work on the design of virtual VR controllers that act and feel more like our own hand. Thank you for your attention. I will be happy to answer questions.
Yes, many thanks. Are there questions from the audience? Back there.
Hi, Jeremy Cooper-Stock from McGill University. I really like the motivation behind this work in trying to get controllers that are feeling more natural and giving us the affordances of everyday interaction. If I understood correctly, you had a vibrotactile or a voice coil actuator inside of the device. Did you consider making use of that to try to augment the perception of compliance? Because I noticed that in the video, you seem to insert little foam pads instead to give that, but you could actually make use of the voice coil by adding slight vibration, and we've actually found in previous studies that even subthreshold vibration can increase one's perception of compliance. So thinking as a nice little add-on, you could actually improve the response in that manner.
Well, I wonder if I understood correctly your question, or is that suggestion? I mean, the soft material is not part of torque. This
right.
is only for,
So can you, if you want to give the user the experience of interacting with a more compliant material, did you consider adding a little bit of vibration with your voice coil?
Yes, I think it's a really good idea. I think we can, tune or calibrate, maybe different materiality or different type of compliance. There is different type of compliance, right? Like rubbers or sponges. So I think we can make different type of compliance. We can, render different type of compliance change the waveform of vibration or duration or the power of vibration, etc., or the latency.
Exactly. I mean, you have a lot of visual cues that are nice, but you can augment those with vibration.
Thank you.
Are there more questions? There's still some discussion going on. Yeah.
Hi, thank you for the great talk. I'm Eisuke Fujinara from Sony. So I saw that a key application, using key application is very good, but do you have any other possible application with this controller?
So actually, because you said you're from Sony, you may know about the traction, the work from Professor Junrei Kimoto.
Yes.
Yes, that uses actually vibrotactile actuator, two vibrotactile actuator to make the illusion of inertia. So I think this controller can do the same. Changing the software a little bit to make the illusion of weight, or yes, yes. Now I have just that thing in mind, but yes, there can be many potentials.
Okay, thank you.
Other questions? I would have one. Did you think about how to integrate that into existing frameworks and what that means to support this kind of controller for designers? So if I'm a game designer and I want to design for this controller, what do I have to add? So how much complexity does it add if I want to support such a device? Do you thought about it?
So your question is the potential application for other controllers like game controller, or
yeah, if I imagine I'm a game designer and I want to enrich. This is a new Vive controller, could be. What do I have to do as a designer to support this controller?
Actually, one really big advantage of TORC is really simple hardware. It just needs for sensor and little bias. Little idle bias and finger capture to sense the lifting force and the vibration actuator. So I think pretty much this hardware setup is pretty much the same. The part it has is pretty much the same with the conventional controller. However, the new combination of them can be used to make TORC interactions. So yes, I think it's really simple and easy hardware setup.
Okay. So if there are no other questions from the audience, let's thank our speaker again.